variances are equal to each other. So we generally don't like testing for covariances. Here's testing for covariances. Let's see if we give this a, is that the test for variance? I don't know. So here's the turkeys with not making the covariance matrices the same. By the way, there's a logical reason why the covariances would be different. Wild turkeys are different than domestic turkeys. Domestic turkeys probably are genetically similar to each other, right? Wild turkeys are probably not at all the same. To assume that the relationship between the variables is the same for the wild turkeys and the domestic turkeys is probably not a good idea. And if you allow the covariances to be different, you get them all right. That's cool. We were back 20 slides ago, we were at the, can I do it? That's the priors one, talking about priors. You will sometimes people see talk about priors. There's the 1 and 1. So using the linear discrimination, we got one wrong there and one wrong there. Using quadratic discrimination, we got better. If you use weaker assumptions, you should get better in general. Not always. But so we did better. I wonder if the cross-validation is coming up. And the cross-validation got 3 wrong here and 2 wrong there. The quadratic assumption means we have to estimate 2 covariance or correlation matrices, which is hard when we only have, how many? 33? Sample size of 33? This is probably a bad idea. And if I'm in court and someone uses a quadratic discrimination with a sample size of 33, I'm going to go, and really, you can estimate those 2 correlation matrices accurately. I have to go, no, I can't, just classifies well. But you get caught. So compared to, so we got 3 wrong there and 2 wrong there. Now I have to go back here.
2 and 2.
What did we get in
2 and 2.
3, 2 as well?
2 in either cell.
2 and 2?
Yeah.
Oh, so perfect. Makes my point. We actually did worse on cross-validation, which suggests that we're overfitting, basically, by letting the covariance matrices be different. And so, again, if I'm in this courtroom and they go, oh, we got perfect discrimination, I'm going to say, well, what happens with the cross-validation? And they go, I don't know, I didn't try that. Well, then they look dumb because they didn't do the cross-validation. And I get to say, well, if you do it, maybe our linear method is different. The guy's going to jail anyway, so, yeah. You are going to get the cross-validation thing. It's more and more common that your classification is biased by the data that you have. You have to run the cross-validation and see what happens. And then it really annoys you because the cross-validation isn't nearly as good. Or maybe it is almost as good. You go, oh, that's great. But the referees, again, are going to ask because they know to ask. Do they know more about the multivariate techniques than you do? Sometimes. When I'm on a social science paper, it scares the crap out of me Because those people know a whole lot about stuff that I don't know much about. The factor analysis people get me.
So, in this example, the linear method didn't classify as well, but the cross-validation was better, right?
Yeah.
And then the quadratic classified better, but the cross-validation did
Not
not
quite
do
as
well.
good, right.
So which one would you use?
I'd use the linear one for sure.
Okay.
Because of the 33.
Okay.
If we actually look at the correlation matrix that's being estimated, that there's no way we have enough data here. If I had 100 or 300 or something like that, then I'd be like, sure, quadratic, why not? But 33 means you have to be really careful about the number of parameters you're estimating. And as soon as you assume this, you have twice as many parameters to estimate. And it's not just one. This is a matrix. This has got sigma 1 squared here, sigma p squared here, and we've got all these correlations in here that we have to estimate. Fortunately, it's symmetric, so you don't have to. It's that many. But that's a lot of things to estimate. And depending on how many variables I have, it gets worse. So that you have to be careful. Not so. In general, we don't like this assumption. But there are other cases, my big data situations where I got tons of data. And then you go, well, why did that idiot? So when I'm reviewing the paper, I'm going, really? They assume that the covariance matrices are the same when they have a sample size of 10,000 in each group. Well, you don't need to. And you may classify, if you get that wrong, so suppose you're if you're in this situation, and you have a sample size of 10,000 in each group, then why would you assume that the shapes are the same when it's obvious from your picture that they're not? I mean, I can review the paper and look at the picture that they made because they knew they were supposed to make a picture, but they didn't actually understand the picture. And the picture, this picture screams, use quadratic discrimination. But they always use linear discrimination because that's what they learned. And so they're wrong. Go, oh, this is why, and then I write the review that says, hey, you should try quadratic discrimination and see if that helps. And lo and behold, they revise the paper and they talk to somebody and they do quadratic discrimination and they have a much stronger paper. Because it was obvious from their picture. I don't have to do it. I don't have to have their data because I can look at their picture and say, oh, here's your problem. This is simplified. Let's go over here. The same thing happens in a treatment and a control when the data looks like this. Something like that. And you look at the plot and go, oh, why would you assume equal variances between those two? This variance is obviously tiny. This one's obviously huge. This is the case that gets me, lots of people love it because you assume equal, and I've showed you these plots before. But just because it's multivariate mess doesn't mean it's not basically the same situation. If the variances are different from each other, then you really want to allow them to be different from each other. Yeah. And in this case, it costs me one parameter to assume that the variances are different. That's nothing. This one costs me a lot more. So I'm not going to go to quadratic here unless I have a lot of data. And a lot, who knows what a lot is? but a lot is not 33. So I shouldn't do it. And although you could argue that oh, you did better. Well, you did do better. Would you classify better in unknowns? Probably not. Because we really don't know how to classify very well based on 33 observations. All right. Other questions? I've been playing with an example. So we'll at least start with it. Where's my elements? So this is a hard classification problem, remember? That we have trouble seeing the difference between the US and Kentucky. And it turns out that some of the variables are actually pretty good at discriminating. So I have to but I also only have 23 observations. So I can't do a whole lot, right? But I can. So what I've been playing with is trying to use all these different methods on this data. And I don't have the perfect example yet. I like my coloring, by the way. Let's see. If you're publishing in an online journal, by the way, I think the bias against online journals is kind of funny.